Okay, let's dive right into this. We're heading back to November 5th, 1983. The setting? A drilling rig called the Byford Dolphin, stationed in the brutal, unforgiving waters of the North Sea. What happened there is still considered one of the most violent and frankly terrifying industrial accidents ever recorded. At the very heart of this disaster is a single, staggering fact of physics. The pressure inside a specialized diving habitat dropped from 9 times the normal air pressure we feel every day, all the way down to 1, and it happened in a fraction of a second. We're talking about an instantaneous, explosive decompression. So that's the big question, isn't it? When the laws of physics are unleashed with that kind of raw power, what on earth does it do to a human being? Well, to figure that out, we first have to become investigators and look at what went so catastrophically wrong with the machine itself. All right, so our investigation starts with the hardware. We need to walk through the exact sequence of events that led to this total failure, a complete breakdown in both the equipment they were using and the safety procedures they were supposed to follow. First, you gotta have some context on this. The men on the Byford Dolphin were what's known as saturation divers. This basically means they lived for weeks at a time inside pressurized chambers on the rig itself. Why? Well, it allows them to live at the same pressure as the deep sea where they work. This way, they can avoid the long, dangerous process of decompressing after every single dive. Now, moving those divers from their diving bell back into their living quarters is a really delicate multi-step process. It's called a transfer under pressure, or TUP. The sequence is absolutely critical. First, you close the bell door. Then, you close the chamber door. This isolates the little connecting tunnel between them. That tunnel is then depressurized back to normal air pressure. Only then, after you're sure the pressure is gone, should the giant clamp holding the bell be released. Every single one of these steps is a critical safety barrier. But on the day of the accident, that procedure just fell apart. The chamber door, it wasn't fully closed. That critical step of depressurizing the connecting trunk, it was never even attempted. And yet, somehow, the final, irreversible step, releasing the external clamp, was taken. In that instant, the only thing holding back 9 atmospheres of pressure was suddenly gone. And with that one single, catastrophic error, the full, terrifying power of physics was unleashed. That pressure vessel was turned into a bomb. Get this. The pressure difference between the inside of that chamber and the outside air blasting through that 24-inch opening created an instantaneous outward force of over 50,000 pounds. I mean, try to picture the weight of an entire industrial truck pushing outwards in a single, violent burst. So what happened? The entire system essentially became a giant pneumatic cannon. The diving bell was launched away from the chamber with incredible force, killing a crew member on deck, William Crammond, instantly. The escaping air also slammed an internal door shut, but it jammed, leaving a crescent-shaped opening for all that high-pressure atmosphere to just keep screaming through. And this brings us to the devastating human cost. 5 men lost their lives, but in shockingly different ways. Tender William Crammond died from the blunt mechanical trauma of being hit by the flying bell. But for the 4 divers inside, their cause of death was the pressure change itself. 3 died from the horrifying internal effects of decompression, while one diver, Troels Hellevick, who was standing closest to that jammed door, suffered what the forensic report could only describe as total body disruption. To really wrap your head around what happened inside those 3 divers' bodies, we need a quick physics lesson on something called Henry's Law. It's actually pretty simple. The higher the pressure you're under, the more gas, like nitrogen, dissolves into your blood and tissues. But when you release that pressure instantly, all that gas comes violently out of solution. The forensic findings here were just mind-boggling. The pressure drop was so fast and so violent, it didn't just cause gas bubbles, like the bends. No, it was powerful enough to literally rip apart the protein structures that keep fats dissolved in our blood. Those fats instantly crashed out of solution, clogging their entire circulatory systems. The autopsy report described it as looking like sizzling butter in their blood vessels. Death wasn't just fast, it was absolutely instantaneous. So the Byford Dolphin was all about immense pressure exploding outward. But there's another side to this coin, another industrial hazard that's just as deadly, but one that pulls inward. It's known as differential pressure, or delta P. Okay, let's break this down because the distinction is really important. The Byford Dolphin was a failure of containment. You had high pressure on the inside pushing its way out. Delta P is the complete opposite. It's when you have high pressure on the outside pushing in towards a low pressure area, like an open pipe or a drain. It creates this invisible but unbelievably powerful suction force. And the forces we're talking about here are just insane. Look at this. Even a tiny 2-inch opening just 100 feet underwater can pin a diver with almost 140 pounds of force. Unmovable. At a 12-inch opening, that force becomes over 5,000 pounds. That's the weight of an industrial vehicle holding you in place. It's an insurmountable, lethal trap. And it's exactly this invisible force that led to the tragic Paria pipeline disaster back in 2022. Now, whenever you have a story this extreme and this bizarre, myths are going to start to pop up online, right? It's just inevitable. So let's take a minute to separate the internet lore from the hard forensic reality. You've probably seen this one. It's the most common version of the myth, and it usually confuses the explosive event of Byford Dolphin with the suction physics of delta P that we just talked about. The official reports, however, tell a very, very different story. Okay, let's set the record straight right now. First, the diver, Truls Hellevik, wasn't sucked through a tiny hole. He was expelled by an explosive force through that 24-inch crescent-shaped opening. Second, the cause was explosive decompression pushing out, not delta P suction pulling in. And finally, while the outcome was horrific beyond words, the term total body disruption is the accurate clinical description from the forensic reports. You know, a tragedy of this magnitude has to force change. It just has to. And the investigation into the Byford Dolphin disaster did exactly that. It revealed critical flaws that led to a complete revolution in diving safety. And this is really the key lesson here. You can't build a safety system that relies on people being perfect all the time. It's impossible. You have to engineer the human error out of the system. So now, modern diving systems have mandatory mechanical interlocks, physical blocks that make it impossible to open a clamp if there's still pressure inside. They have external gauges so anyone can verify the pressure, and fail-safe doors that actually use the internal pressure to seal themselves even tighter. The investigation also really highlighted a concept that's now famous in safety circles. It's called the Swiss cheese model. The idea is that big disasters rarely happen because of one single failure. They happen when the holes in multiple layers of defense, things like obsolete equipment, a noisy work environment, and simple human fatigue, all line up perfectly, allowing a disaster to slip right through. And despite all the lessons we've learned, this timeline is a pretty sobering reminder that pressure remains a constant and totally unforgiving hazard. From the original disaster in '83 to another fatal accident on this very same rig in 2002, and then the Delta P tragedy at Paria pipeline in 2022, the danger is clearly always there. And that really brings us to the final, powerful takeaway. The forces of physics are absolute. They are unforgiving, they don't care if you're tired or if a procedure is confusing. And the ultimate lesson from the Byford Dolphin is that our safety systems have to be engineered to be foolproof, precisely because the people operating them never can be. So I'll leave you with this to think about. The divers on the Byford Dolphin were killed by a force they couldn't even see. What other invisible forces, whether they're physical, electrical, or chemical, are all around us every day, held in check only by the safety systems we design, build, and hopefully always maintain?